This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. And I hope by now most of you managed to submit assignment 1 through LMS. But I heard a lot of people had difficulties with turning it in and everything else. If you experience any technical issues submitting it, you can still submit it today via email directly to our tutor, Hannah. Okay, if you have any problems there, just make sure you submit it to her directly, just a Python notebook, okay? And today we're going to continue talking about networks. So on Wednesday, we covered a few basic concepts and types of graphs. And today we'll focus a little bit more on analyzing those graphs, those networks. And we'll focus on characterizing what we call complex networks and how do we fit them in specific categories or classifications and how we generate synthetic graphs based on graph models. So just a quick recap from what we studied last Wednesday is that based on different node and edge properties, based on the decisions we make to how to model our graph, we can have different graph types. For instance, depending on whether an edge has a direction or not, we can have undirected or directed graphs. We can have acyclic graphs. An important undirected acyclic graph are trees. We can have weights on edges, for instance, trying to, for instance, model the strength of the relationship. So we would have then weighted graphs or unweighted graphs. And depending on the number of edges, we can have either sparse or dense graphs. And this goes on and on. So there are different graph types. And based on these graph types, we'll choose the most appropriate data structure to store these graphs in a computer, for instance. We mainly talk about two data structures. One of them is an adjacency matrix, which is very interesting for dense graphs, and adjacent list, which is more adequate for sparse graphs. And we also talked about a bit about two algorithms to do graph traversals, how we then navigate through these graphs. And the two algorithms were deep first search and breadth first search. So deep first search was an algorithm that it's more adequate to ask the question, is there a path between a given node A and B? And it uses a specific type of data structure called a stack. And breadth first search is more adequate to identify shortest path between nodes. And instead of a stack, it uses a queue. So today we're going to focus on characterizing these networks and extracting information from them. So why do we need network analysis? So networks will basically try to shed light into the link between the microscopic interactions of the elements of that network and try to understand emergent microscopic collective phenomena, patterns, and dynamics of that network. So that's why we try to model complex systems as networks. And we basically want to study how entities, our nodes in our graph, interact, and at a small scale, how they organize themselves and collectively bring up non-trivial structures and behaviors. And basically, we will aim to understand networks to try to come up with basic design principles, for instance, to better understand the biological phenomena that we model. And for that, we use complex system modeling. And in order to characterize networks, we can ask a bunch of different questions. For instance, we can start asking the question, is my network connected? And for that, for instance, we can ask the questions, if it's not, how many different components it has? And we'll go through each of one of these questions in detail in a bit. We can ask a different question as well. Looking at our network, we can ask the question, how far are nodes on average apart? And for that, we're going to introduce two different metrics. One is diameter, and the other is average path length. Another different question we can ask is how dense our network is. We already talked about different data structures that are more appropriate for dense and sparse networks, but how dense? How do we quantify network density? And basically, we'll try to do that by assessing the number of edges over the potential number of edges, and also assessing a new metric called clustering coefficient. Okay? Another option would be asking how diverse is node connectivity. So we already talked about node degree. So node degree is basically how many neighbors each node has, how many connections. And we'll talk about node degree distribution and how different networks vary in node degree distribution. And we will use all of that to try, for instance, to identify parts of the network or individual nodes that are more central or more important. And for that, we'll comment on centrality metrics, which are quite important. We'll focus on local and global centrality metrics. And later on, we will also try to understand our network and categorize them in specific models. And in order to compare our networks, we will try then to generate artificial networks, following the same patterns as our own, to try to classify them. So let's start with the first question then. Is the network connected? So we say a network is connected if there is a path from every node to every other node in the network. Okay, for instance, that network in the example, not sure you can see from there, but we have this huge component here and another one that is separated there. So if I can't go from here to here, that means their network is disconnected, and a component in that case is a subset of mutually connected vertices without connections from the rest of the network. And what that means is a maximal subset. For instance, this subset of nodes here is a component, is a maximal subset of nodes, meaning if I add any other node here, it won't longer be connected. So that's the meaning of maximal subset. And for instance, in that network, we have one large connected component and a couple smaller ones there. And this could have implications for the type of analysis we want. We might not want a disconnected network, for instance, for the analysis. And that, of course, reflects, for instance, on the adjacency matrix if we're modeling the graph like that. And based on what we've seen on Wednesday, how would then we go about to identify how many graph components we have on our network? How would anyone do this? Can I get an example? How would you identify, given a graph as an input, how many components does this graph has? Grace, how would you do it?
I guess you could do like a breadth-first search or depth-first search. Just pick a random node to start search as many nodes as you can. And then basically you probably have a situation where you return to your original call and you have to jump to a node that wasn't connected before. And just count how many times you do that first call jumping.
Yeah, that's a really good way to do it. So basically, adapting graph traversals. As long as you keep track of the nodes that have been visited, if you start a random node, you traverse as much as you can, marking them as this is on, let's say, connected component 1 until you can't anymore, and then you start from nodes that haven't been visited until you have the number of connected components. Yeah? That's how you could do this. And then you have the number of components of your network. But what about how far nodes are apart? And that has to do with something called diameter and average path length, which are very important metrics. So we already established that a path between two nodes, A and B, is an ordered list of k consecutive edges. Let's say, considering this graph here, a path from A to B will be a connected sequence of edges, from starting with A, with intermediate nodes, finishing in B. And the path length, and from now on when I mention path length, I'm interested in the smallest path length, will be the number of edges in the path. And that's for an unweighted graph. Okay? And for instance, in this case, considering that's the smallest path, we can have the shortest path from A to B, we would have 1, 2, 3 edges, 3 hops from A to B. And that's the path length, which in this case is also the shortest path length. So the average path length of a network is one way to characterize it. So it will basically be the average path length between any two pair nodes in the graph. Okay? What's the implication of that for the network? If you have a really, really low average path length, if you can think about it, how information flows in a network, you can say that information is spread really quickly. So the average path from one node to the other is small. And that have different implications, while network diameter will be simply the maximal path length between any two nodes. So the longest distance, okay? Keep those in mind. The other question we can ask is how dense is the network? And for that, we have two different metrics. The first one is graph density, which is simply given a graph with n nodes, is the proportion between the maximum number of edges we can have, and that's n times n minus 1 divided by 2 for an undirected graph. Divide, and then we consider then the fraction of edges that are present. So let's say out of 20 possible edges, we have 5, therefore we have 25% of graph density. Alternatively, and that's a very simple metric that doesn't tell much about how structured the network is, because you can have nodes that are really, really dense and nodes that are not that dense. A different way to assess how dense the network is with transitivity. So transitivity will tell that if an object A is related to B and an object A is related to C, that implies that B is also related to C. This is the general statement for transitivity. How we measure transitivity in a graph is basically using a metric called clustering coefficient. And the idea of clustering coefficient is basically measuring how strongly neighbors of a node are themselves connected. So looking to my neighborhood, how connected they are. And basically, we would have two types of clustering coefficients, local and global. So one per node and one per graph. So basically, let's consider blue as our given nodes, and we're interested to ask how well connected my neighbors are. If my neighborhood is a complete graph, or a clique, meaning all possible edges are there, we would have a clustering coefficient of 1. For instance here, so I have 1, 2, 3 neighbors, and my neighborhood is a clique, so I have all possible edges there. So 3 out of 3, meaning our clustering coefficient equals 1. In this case, my neighbors only have 1 out of 3 connections, therefore the connectivity is 1 out of 3. And when they don't have anything connecting them, connectivity equals to 0. So basically, the formula for node clustering coefficient would be basically the number of observed edges in my neighborhood divided by the total potential edges. And for the graph, we can average them out by the number of nodes, and then we have an average local clustering coefficient for the whole graph. And let's try to calculate that, for instance, for a given node A. So I'm basically trying to understand how strongly connected are my neighbors, and what's the proportion of connections I see out of the total amount. For instance, let's consider then node A, which has 1, 2, 3, 4, 5 neighbors. What's the clustering coefficient for A? How many possible connections I can have with an undirected graph of 5 nodes? The other grace. So I have 5 nodes. How many connections I can have? How many edges on an undirected graph? From 5 nodes. So basically assessing my neighborhood. Okay, so neighborhood there has 5 edges. If it was a clique, how many edges it could have in total? 20? Almost, right? So we do combination of 5, 2 by 2. How many pairs in 5 we have? Right? That would be 5 times 4, 20, divided by 2. That's because it's undirected. If it was directed, that would be 20. And how many connections we have here? We have exactly 6 connections. So basically, clustering coefficient will be 6 out of 10. 60%. Okay? And if you go doing this for every single node and averaging them out, you have a clustering coefficient for that graph. And then we can ask the question, how diverse is node connectivity? And we already mentioned about no degree distribution, but this varies a lot from graph to the graph. So no degree distribution will tell you basically, we can represent this basically as a function or a histogram. If we represent it as a function, let's say pk will tell us about the probability of a given node have a degree of k, so having k neighbors. And this is very interesting to show the spread around the average, for instance, but it also represents really well how diverse networks can be. For instance, a random network will have something like this. So we would expect that on average, nodes have k neighbors. In that case, 5. But that's not always the case. For instance, real networks, for instance, the East PPI network looks like this. So here we have frequency, for instance, or that probability, and the actual node degree. And this is basically telling us there is a lot of nodes that have only few connections, and only a few nodes have a lot of connections. So basically, this is pointing to the presence of hubs. And this could be quite interesting. So identifying hubs on network analysis could be point you to the direction of important nodes of the network that you might be interested to access. And usually when you have this kind of a logarithmic decay here, we usually represent the node distribution as a log plot. So logging both y and x axis. Okay? And with that, if it's a logarithmic decay, we'll have a straight line. So this is called actually a scale-free network. Okay? Because the node distribution, the node degree distribution is following a power law distribution. And we'll chat about that in the end of this lecture. And with that information, we would like to assess, I mentioned that identifying hubs is quite important, but how do we actually identify if a node is central or important to a network? And for that, there are different centrality metrics. So how do I know whether a node is important or not? We can do that in different ways. For instance, node degree is a local criteria. So I basically look into my neighborhood and say a node is important if it has a lot of connections. Okay? That could be valid depending on the network you're assessing. But there are also global metrics. For instance, we're going to talk about betweenness centrality, closeness centrality, and eigenvector centrality as well. And starting with degree centrality, basically we're saying that nodes with more connections are more central or more important. And basically, a degree centrality for a given node I would be either the degree of the nodes, or we can either normalize it based on the maximum degree of that graph. Okay? For instance, in this graph, the most central one, based on degree centrality, would be the nodes with more connections or more edges. However, is degree centrality always a good metric? That depends on what you're assessing. For instance, let's say instead of 3 nodes this side, you have 1,000. Let's say instead of 3 on this side, you have 1,000. So basically, you have one node connecting 2 large subgraphs of 1,000 nodes each. What happens if you remove this node from the network? You used to have one component, now you have 2. So you basically disconnected your network with removing one node with only 2 neighbors. Yeah?
People have analyzed trees by taking out the node and viewing the impact.
Yes, yes. There's a very well-established way to analyze node importance. Is, for instance, if I remove it, does it become disconnected? And when it does, is actually, there's a specific name for this node, which is called a bridge. So when you remove a node and you increase the number of connected components, you have a bridge. So yeah. And that can affect all types of information, for instance. Okay? So that can upset the degree distribution, so on and so forth. So yeah, one other way to assess importance is actually removing it and recalculating the properties. And for instance, when degrees centrality fails, one of the situations is, as mentioned, keeping the network connected. And for instance, the likelihood that information originating from somewhere in the network reaches a given node. And that's the same principle of bridges as well. And for that, we need global metrics that will take into consideration the whole graph. And the first one is betweenness centrality. And the intuition behind betweenness centrality is information flow. So basically, with betweenness, we're asking how many pairs of nodes would have to go through a given node in order to reach each other in a minimum number of steps. In other words, I'm asking how many shortest paths goes through that node. Okay? So information will try to flow for the shortest path. A central node based on betweenness would be then a node that is involved in a lot of shortest paths. Okay? So basically, betweenness centrality is the proportion of shortest paths that pass through a given node. And that's a metric for a given node. And basically, it would be the number of shortest paths connecting two nodes, any two nodes. Out of those, how many actually go through node I? Okay? And how would I then define shortest paths in a graph? What can we do to define short paths in a graph? What kind of traversal? Breadth, yeah? And basically, calculating this proportion will have betweenness centrality. And this graph, for instance, is colored based on betweenness. So nodes on the border there, they have low betweenness centrality, and nodes in between have high betweenness centrality. And another metric that it's also global is closeness. So sometimes it's more important to be in the middle rather than in between. So that's the main conception behind closeness. So instead of being part of shortest paths, with closeness, I want to say this node is important if its average distance to the rest of the node is small as possible. So basically what I say is I'll calculate all shortest paths from one node to all of the rest in the network, and we'll calculate what's the average shortest path from it. And then we'll call the closeness centrality as being proportional to the inverse of the distance from one node to the rest. So nodes that have small distance from the rest will have a higher closeness centrality metric. And on the same way, this graph is colored by closeness. So it's easy to see if you have a regular graph that you can fit in 2D, that things in the middle will actually have a larger closeness centrality. But the interesting thing is, for instance, on this graph here, this graph is colored by closeness, but the size of the node is colored by degree centrality. And in a few cases, for instance, they match. So you have large nodes with really red closeness values, so they're central based on both metrics, but sometimes you have really small nodes that are really, really red. So these could be potential bridges, for instance. So they are in the middle of the network, but they don't have many nodes directly connected. That's why a global metric might be important and interesting to assess. And of course, we can then normalize this based on the number of nodes or distances we have. And the last one I'd like to mention is eigenvector centrality. The idea of eigenvector centrality is measure influence. It's slightly different from the others. And the mathematical rationale is actually, since we can model our graph as an adjacency matrix, we can then do this operation on it, which is basically a geometric analytics operation. Is given a matrix, square matrix X, we can write X as follows. There is a vector, matrix A, we can then identify a vector X, which is called eigenvector, such that the product AX equals a scalar multiplied by X. This has to do with matrix decomposition. We'll see that in a few weeks. But basically, in practical terms, eigenvector centrality measures influence and measures nodes importance in the following way. So it generalized degree centrality, incorporating the importance of the neighbors. So it's saying that each edge is a vote. So if I have a connection, so that's a vote, but that vote is weighted by the importance of my neighbors. So it's based on recommendation. And that's quite important given Something we use in our daily lives, the Google search engine, is actually built upon that idea, okay? So it's called the PageRank algorithm that was proposed late 90s by Sergey Brin and Larry Page, the co-founders of Google. And basically what it does is it will say a given web page is important, depending on how many links it has, but also who it's linking it to. Let's say you have your web page and you have your PageRank. If suddenly Bloomberg or BBC also have a link to you, you have a recommendation, and that will increase your PageRank proportionally to their importance as well. So it's a way to, instead of just considering the degree, all edges as the same, we'll say that some edges are more important, okay? And for instance, in this is just a very old Twitter network. This is just saying that Barack Obama is quite influent and very central, not only because it has a lot of edges connecting to it, but also the important edges are connecting to it as well. So basically, considering edges as votes, as weighted votes. And finally, how do we classify our graphs into specific categories? How do we know how the graphs behave? And for that, we can compare our graphs with automatically generated models, and that's quite important. So the first network model that I would like to present is regular networks. So let's imagine then a lattice model. And we'll also talk about random networks, and for that we'll have the Erdős-Rényi model. We're going to briefly talk about small world networks with the Watts-Strogatz model, and scale-free networks that I already mentioned today with the Albert-Barabasi model. So starting with regular networks, basically a lattice network is usually structured in a geometric, either 2D, 3D, 4D background. And basically we can create a lattice network saying we are going to connect every node that is nearest to each other. So we have a Euclidean physical distance between them. That makes sense, for instance, if you're considering roads, if you're considering actual physical networks. And one type of regular network is the ring lattice. In a ring lattice K, we're going to first lay out all the nodes in a circle, and we'll connect it to the K nearest neighbors. So a ring lattice with K equals 2, I'm going to lay them out in a circle, and I'm going to connect them to the neighbor on the left and the neighbor on the right. A ring equals K, we will also connect it to the second neighbor, okay? And we'll keep going. So every single node on this network will have a degree equals to K, okay? So uniform degree distribution. And if we think about those two properties I mentioned, one of them being average path length and clustering coefficient, how would these be for these type of networks? For instance, these networks have a really, really high clustering coefficient. So their neighborhoods of the nodes are very densely connected. For this case, for K equals 4, clustering coefficient is 0.75. However, they have a high average path length as well, which in this case is proportional, inversely proportional to the number of K. And that's fairly easy to visualize if you think with K equals 2, for instance. Let's say you have a ring with 1,000 nodes, and you consider K equals 2. That means you're only connecting each node to the left and the right. What's the average path length on that graph? So on average, you need to reach one node, you might need to go from one way or to the other, right? So you only have two options. You go clockwise or counterclockwise. So on average, you need to hop 500 times to reach a node on average. So that's one important aspect of regular networks. So you have a lot of structure. Their neighborhoods are highly connected. However, information takes longer to flow, especially if K is a small number compared to the number of nodes. Okay? Keep those information in mind. Random networks, on the other hand, we don't have a specific number of degrees per node. So edges are formed randomly. So we have a uniform probability of a given edge existing or not. And one way to automatically or synthetically generate random networks is using the Erdős-Rényi model, which will generate random graphs considering two properties, number of nodes and a probability of connecting them. So, for instance, if we have this graph here with a probability of 0.18, for each potential vertex, let's actually consider that the probability to generate an edge or not is 1 out of 6, okay? So, and we have, let's say, 17 nodes. 17 nodes will have 17 times 16 divided by 2 potential edges. For each of those, if my probability is 1 out of 6, I basically will drop a dice. If it lands on 6, I create the edge. Otherwise, I don't, okay? And that's basically what happens with that model. And then edges are randomly attributed with n nodes and a given probability p. And what would be the properties of this network? Would this network have a high clustering coefficient or a low clustering coefficient, a high average path length or a low average path length? If you recall from the lattice, a regular network, it's high clustering coefficient, high average path length. Information takes a while to go from one side to the other, but it's very well connected, at least the neighborhood. On this case, for random networks, on the other hand, we have a low clustering coefficient. Clustering coefficient is as low as the average probability, so the probability of neighbors being connected is usually quite low. However, we have low average path lengths, which empirically they can be deduced as being logarithmically on the number of nodes, meaning you can find shortcuts on random networks. That's one of the advantages of on random networks. Information flows very quickly. So we have on regular networks high clustering coefficients and high average path lengths, and random networks we have low clustering coefficients and low average path lengths. And there comes social analysis and social graphs with the small world phenomenon with the Milgram experiment. So we've been talking about small world networks since the 1960s, and that probably started with Milgram's experiments. And what's that all about? So they were basically interested in understanding what's the probability of two random people selected that they would know each other. And what they've done to try to assess that was the following. So they selected around 300 people from Nebraska in the US, and they said, I would like you, here there is a correspondence I would like you to deliver. And this correspondence, I only tell you the first name and last name, and it's a stockbroker in Boston, Massachusetts. I want this to go from here to here. And if you don't know the person, I would like you to pass the message to a person you correspond with on a first name basis, who you think is closest to the target. That could be a person geographically closer or someone that is a stockbroker but not necessarily in Boston. And that this person will continue then forwarding the message. And they're interesting to understand how many forwarding steps, hops, it would take for the letters to arrive there, if they're going to arrive. And interestingly, letters that arrived to the destination only took on average 6 hops. And considering the scale of the country and how many people are there, that gave rise to the famous expression 6 degrees of separation. What does that tell us about social networks in terms of the average path length? They have a very, very low average path length. Even though we have a lot of nodes, we have millions and millions of nodes, and we still have a really, really small average path length. And that's one aspect of small world networks. They have low average path lengths, but also they're really well connected. They have high clustering coefficients because transitivity holds for social contexts. For instance, a friend of a friend, it's also frequently a friend. So A and B are connected, B and C are connected, meaning A and C are likely connected as well. So small world networks have these two properties. So high clustering coefficients, considering that a friend of a friend is usually a friend, meaning the clustering coefficient of small small world networks are considerably higher than random networks, and also low average path lengths. So the 6 hops between any people in the world. And so the average path lengths of small world networks are actually comparable to those of random networks. And how is that possible? How we can then create artificially a graph that is a small world. And based on these two properties, actually, you can identify, let's say you model your graph. You can then try to characterize it. For instance, let's say your graph has 1,000 nodes, 200 edges. You can then try to generate a random graph with the same properties, with the same number of edges and nodes. You can generate lattice with the same properties as well, and compare these two properties. That's how you characterize your graph as a small molecule, as a small world network. Sorry. And not only social networks have been characterized of small world networks, but also different biological networks. For instance, neural networks in C. elegans was one of the first to show this type of property. And the question then is, how do we artificially generate a small world network? And that's with the Watts-Strogatz model that was proposed in the 1990s as well. So the basic idea is, considering a regular lattice, a ring lattice, we will do a rewiring of this lattice randomly. And the basic idea here is to add shortcuts. And what it does is, so when we go from a regular lattice and we keep rewiring it, it will rapidly decrease the average path lengths, including those shortcuts. And if we keep going, we end up with a random network. However, if we keep the number of rewiring connections low, we keep a high clustering coefficient. So there you go. We go from a regular network to a small world network. So a small world network can be interpreted as a hybrid network between a regular lattice and a random graph. And the last type of network that I'd like to mention is the scale-free network, which is quite common. So this comes from the observation that a lot of real-world networks, they contain hubs. Naturally, they contain hubs, which are highly connected nodes. And what this does is generating a skewed node distribution. So networks for which the degree distribution follows what's called a power law actually are called scale-free networks. So the probability of nodes having degree k actually decays exponentially, meaning we only have a few nodes with a lot of connections, and most nodes have only a few connections. So plotting this in log scale will give us a straight line. And when you compare it with a random network, we will identify actually hubs that are very important. For instance, that's the case of protein-protein interaction networks. And one important thing about scale-free networks is how they grow. They grow by a process called preferential attachment, meaning it isn't a uniform distribution. When you add a node to the network, new nodes will prefer to attach to these hubs, to the well-connected. And that's how the Albert-Barabasi model works, by preferentially attaching new nodes to a given node that is well-connected. Okay? And this is basically how you can characterize different networks and different network models and identify importance in that networks and the different node properties. And if you'd like to know a little bit more about network analysis and get into it, there are a few graph tools and libraries that are very important. For instance, for graph visualization, there is Cytoscape. Not sure if any of you have heard of it, but it's a graphical user interface graph editor. It also provides analytical tools for calculating clustering coefficients, average path lengths, and also clustering networks, and so on and so forth, which is a scheme of what you see is what you get. So you actually, as you make changes, you can see it. And also, if you're developing things for the web, there is the D3JS, which is a web-based rendering network tool, which works really well as well. And if you're interested in calculating properties, there are Python-based networks. One of the best ones, I believe, is iGraph, which is cross-platform, open source tools that are available in Python, R, and C++, and more recently, people have been using NetworkX. I definitely encourage you to take a look at these. They're quite important tools and very simple to use. And that's it for today. Thank you very much. Hi.
With like code has submissions. I think the multiple submissions are turned off. That's the problem. The problem is like not the submissions. Like
You can't do. Yeah. The problem is, once I created it, I couldn't change. I couldn't find it anywhere. So I'll try to check what happened. There isn't an option to recreate it. And if I delete it, everybody that resubmitted won't have it. If you need to resubmit it, though. Yeah. For assignments, so I'll make sure it's available there. Sorry about that.